All right, if you saw the previous video talking about how to calculate or balance the oxidation reduction reactions, now we're going to go on and talk a little bit more about some good old electrochemistry. So showing here is a picture of a voltaic cell, sometimes called a galvanic cell, but you have two dissimilar metals, in this case zinc and copper, and you have them connected. You have them connected via a wire, and as you go through, it does work. So going through either in this showing a light bulb, or you can put a voltmeter there. Also, the two solutions, you have a salt bridge. The salt bridge has something, usually potassium nitrate. It's to balance the charges. So the zinc is the anode, and I remember this as the anode corrodes. So the anode corrodes away. It is the source of the negative charge. So the anode, the electrons flow from the negative, and they go towards the cathode, the positive source of positive charge, and the cathode grows. So the cathode is going to grow. In this case, more copper metal will absorb on the cathode. And the salt bridge is important because the negative nitrate anions, or whatever the negative ion is in the salt bridge, will move towards the solution of the anode, and the positive ions will move towards the cathode. And because the solution is losing positive ions, it needs to have the charges balance. So a couple things. If you ever look at current flow, if you study it in physics and electronics, we view it as the positive charge moving. It's actually the negative charge moving. So we know this now. Why did Ben Franklin pick the positive charge? The positive terminal is the one that sparks. Is probably I would imagine is the reason why. So if you look at a diagram, I'll show you one later. It's actually drawn incorrectly, but at least we're consistent with our mistakes. So also electrons, as they move relatively slowly. I mean, it's in a linear fashion. I mean, they're moving pretty fast, but in a linear fashion, they move about on the order of 10 to the minus 5 meters a second. So you can see that's 1/100th of a millimeter. So it takes a long time for electrons to move along the wire. What about the force? The electromotive force in this, that moves at the speed of light. So the electromotive force that connects wires, that does move at the speed of light. It has to deal with transfer of photons, and photons move at the speed of light. So keep that in mind with the electrons. They're not, at least along the wire, they're not moving all that quickly at all. Whereas the force is moving the speed of light. And okay, so this cell here, this one as written would have a voltage, assuming it's a standard, meaning 1 molar solution, would have a voltage of 1.1 volts. And a volt is a joule per coulomb. It's the energy per each electron. So I'll go over that in a second. Also, the overall potential of the cell is the anode plus the cathode, and we'll go over this in a little bit. So now, one thing with this, the electromotive force with metals, it is an intrinsic property. So it does not matter how much stuff you have. So let's say I get one of those standing pools, and I get a car-sized hunk of zinc, and I get a big salt bridge, and I connect the two containers, and I get a big container of copper sulfate, and or copper nitrate, I guess in this example, and I get zinc nitrate, put it all in 1 molar, big amounts, and I put another hunk in there, and I take a wire, and then I connect them up, thinking, oh, this is going to be really exciting to see how much voltage is going to be in there. If I had a huge system, it's still going to be 1.1 volts. So it doesn't matter the size. And if I have a zinc atom and a copper atom, or +2 ion, and I do the same thing with just 1 atom and 1 ion, it is still a potential of 1.1 volts, 1.1 joules per coulomb. So does not matter how much stuff you have. And so where is the chemical reaction happening? The anode corrodes. That's the oxidation reaction, and the cathode grows. That's the reduction reaction. There. So some things that if you see with electronic circuits. So if you look at one, like here's an example of a drawing of one. So a volt is a joule per coulomb, And an amp is a coulomb per second, so charge. Coulomb is a charge. So think of electricity flowing like water flowing. The amperage is how much water is flowing. It's a current, and the voltage is the joules per coulomb. That's how fast the water is flowing. How much kinetic energy the water has in a river. That would be like how much energy the electrons have in a wire as it's moving. Another thing, power. Power is the voltage times the current. Gives you joules per second. That's a watt. A watt is energy divided by time. So if you wonder what watts are in terms of electricity and these kind of things, and the battery. So this is shows the symbol for the battery. The batteries, at least in the circuit diagram, show the positive charge is moving. It's actually really the negative charges. But the squiggly line is known as a resistor that resists current. The capacitor, that's the two lines that stores energy. A line to a three part, that's called the ground. That's a ground to the circuit. A squiggly line is called an inductor, and the smaller end of the battery is a negative terminal. When you have alternating current, at least here in the United States, our plugs. The positive hot wire is the one that's the small one. The bigger, flatter one is the negative, also known as the neutral, and the ground is the circle, at least here in the United States. So different countries have different outlets, of course. But that's not in this part is not in the class. This is outside the class. So the standard cell potential is the oxidation potential plus the reduction potential. So, and the oxidation potential is the opposite of the reduction potential. So what do we do? How do we get all these? We actually have gone and we've tabulated all of the standard electron. These are the reduction potentials for everything. It's what it is. It's relative to hydrogen forming or acid forming hydrogen. So we picked a zero, and we picked acid forming hydrogen as our zero. And now we relate everything else to that. So lithium is got the highest oxidation potential, and it's the best reducing agent. And fluorine has the highest oxidizing potential of all of them. So this is the standard reduction potentials here, and you flip them. So for so these are reduction potentials. If you want the oxidation potentials, it's just the opposite sign of it. So let's use these for some of them. So look at this here. Use a tabulated standard electron potentials to calculate the standard cell potential for this reaction at 25 degrees Celsius. So we have aluminum plus nitrate plus 4 acids makes aluminum plus 3 plus nitrogen monoxide plus water, 2 waters. And if you look at the standard cell potential, the reduction potential of aluminum is 1.66, and then the nitrate, if you look at the aluminum, let me go back up to the chart. Aluminum plus 3, so this is the reduction potential right here, and it's minus 0.166. So this is the aluminum potential right there. And we're going the other way, so because of that, it's positive 1.66. And all you got to do is just add these together. So 2.62 is the solution there. So that's the overall E0 is equal to the E0 cell. I'll get rid of the lines. That looks confusing. So that's the E0 cell for this. So you just straight out add them together. Okay, and also you can use this to predict the signs. So equation we're going to talk soon is delta G0 is minus n, the number of moles of electrons transferred, F, Faraday's constant, E0 cell. So either way, if the E0 cell is positive, it's spontaneous. The reaction is spontaneous. If it's negative, it's non-spontaneous. So this is opposite of delta G. If delta G is negative, it's spontaneous. Positive, non-spontaneous. So E0 is opposite of each other. And let's look at these. So iron and magnesium plus 2. So we have iron and magnesium plus 2. And we have, I have to delete these. So we have irons. Where are we going to find iron? Iron you can find here and here, and magnesium here. So magnesium to have this, the reduction potential is negative 1.18, and since iron is above it, so you will not be able to have iron in any way, shape, or form be able to overcome that negative 0.18. You have iron here at negative 0.45 and then minus 0.0036. So the iron metal, by giving up its electrons, going the other way, the oxidation will not be able to overcome that reduction potential. And because of this, the iron, I'm going too far. The iron is non-spontaneous. The E0 is going to be negative. Now let's look at iron and lead plus 2. So iron and lead plus 2. Here's lead plus 2. So now the iron here, in this case, iron can go to lead or iron plus 2 and then give 2 electrons to lead. So actually in this case here, the E0 is positive. So yes, this chemical reaction can happen. So it will in fact work out. So which metal dissolves in nitric but not hydrochloric? So iron actually, if you look at this, iron is below here. So iron is here, and it's below the hydrogen. So all these metals will dissolve in iron. And if you look at the metals that will not dissolve, all these metals will dissolve in hydrogen acid. The ones that won't dissolve in simple acid, these are also the expensive ones. You got copper, silver, and gold up here. This is a partial list. There's also platinum is even more unreactive. So, but then you have nitric acid. So the nitric acid is, so nitric acid has both nitrates, ions, and acid ions. And where's nitric acid? Nitric acid is here. So here is the one where nitric acid has both hydrogen and nitrate. So it has hydrogen here and nitrate here, so just like in nitric acid. So because of that, silver and copper will dissolve in nitric acid, but not in other acids. Gold will not dissolve in nitric acid, or, gold. So this one is, so this is the metal. So silver and also copper are the two choices there. Gold is really hard to dissolve. You have to use something called aqua regia. So aqua regia will dissolve gold. That's a 3-to-1 mixture of nitric to hydrochloric to get that to react. Okay, I mentioned this equation before. We have the Gibbs free energy is equal to minus NF E0 cell. N is the number of moles of electrons transferred. And F, this is Faraday's constant, 96,485 coulombs per mole of electron. And a joule is a volt is a joule per coulomb. So, okay, so let's go ahead and solve this problem. And in doing so, you can see, you look at the reduction potentials. So these are the reduction potentials for iodine and bromine. And is this reaction spontaneous, as you're asking? So we're going to figure out, the way to figure this out would be figure out the delta G. And we'll figure out the delta G and figure out if it's spontaneous or not. But we can tell if it's spontaneous from the E0 cell anyways. The number of moles of electrons transferred is 2. So we're having, we have the common denominator of 2 and 2, and the common denominator between 2 and 2 is 2. And E0 cell, so we have iodine going as written. Bromine's going the other way, so bromine is going to be the negative of this, right? So, because look, we're going bromide to Br2. So in this one, we have Br2 going to bromide. So we have to take this the other way around. We have to take the negative of that. And in doing so, we get the E0 cell to be minus 0.55 volts. So now we apply the delta G. Delta G0 is minus NF E0 cell. So minus 2 moles of electrons then Faraday's constant, 96,485 coulombs per mole electron, and then 0 - 0.55 volts is a joule per coulomb, right? So, and you throw this all in your calculator, and in doing so, and notice everything cancels out except for joules, and you get 1.1 times 10 to the fifth joules. And since which is a positive number, if delta chi is positive, this means non-spontaneous. Non-spontaneous. Spontaneous. So here is our delta G, and since it's a positive delta G, it's a non-spontaneous chemical reaction. So why don't you try this out and see if you can figure this one out. Hint is it's the opposite of the other one that we went. So, okay. So we got more coming up for you.